Great. Thank you very much, Christine and Kayan, for providing these talks. We're now coming to the live Q&A, and the rest of the tutorial will actually be live. So we are running a little bit behind schedule, but I definitely want to take the chance to asking some questions that came up to Christine and Kayan. Maybe I can ask with you, Christine. So you mentioned mediation analysis, and this seems to be striking as like a framework or a method that should be applicable in our context of medical imaging and really be like interesting in a way that we really want to understand these mechanisms of disease. Can you maybe give some examples, or do you know of any work where this is directly applied to medical imaging?
Definitely. So Martin Lindquist at Hopkins has some really cool work using the brain as a high-dimensional mediator. And so he studied pain. And in his study, they actually, the participants wore some kind of device that actually burned their wrist, either at a low intensity or a high intensity. I don't think I myself would sign up for this study, but some people did. And the outcome was the individual's self-reported pain ratings. So how much did the low heat and the high heat hurt? And he looked at how that effect of intensity of heat on pain ratings or perceived pain, I guess, it was mediated through the brain. And that was a really challenging problem because the brain is so high dimensional. And so he came up with a method that was able to account for the high dimensional nature of the brain as a mediator. Some other examples would be if you're interested in the brain as an outcome. For example, if you're interested in studying the effect of prenatal drug exposure on the brain structure or function, that effect, especially if you're measuring the brain much later in time, so when the person is, say, a teenager or an adult, that effect is probably mediated by a lot of things. You might want to study how that effect is mediated through, say, education or social determinants of health or socioeconomic status.
Great. The first example sounds painful, but this is really exciting, I think. There's a question also coming in for Christine. How would the adjustment strategies that you described scale to scenarios with many confounders and possibly non-binary confounders?
That's a great question. And that's the beauty of the propensity score. So under certain assumptions, if you correctly specify that propensity score, it's another name for it is actually the balancing score. If you look at Rubin and Rosenbaum's work on this propensity score method. So it reduces the dimension of those confounders if you specify it correctly. And the beauty of it is that these days when we have access to very flexible models, we can throw in a lot of variables and use a machine learning model that's very flexible to try to correctly specify that propensity score and then just condition on that in our estimate of causal effects.
Right, so that intersection of propensity score estimation could be a nice link to machine learning and deep learning, I guess, in particular. I've seen some works trying to use neural networks to do propensity score matching. Absolutely. Great. Kayan, I have a question for you as well. There's a question about the ambiguities that you mentioned. So in the graphical models, you had this nice example where sometimes you cannot really identify which of the directed graphs is the right one. Now, in a medical imaging setting, again, I mean, is there work or any hope that we can use the data that we have, maybe in a neuroimaging study, to figure out what the right model is?
Okay. Thanks for the question. So I guess I mentioned that in the context that the Bayesian network is not enough, but sometimes you can break that ambiguity based on, like, for example, common sense. So let's assume, for example, that you want to measure the effect of, so that you have multiple variables and one of your variables is genetics. So if you have a genetics, you know that the gene causes variation in the brain because you're born with it. And so it doesn't really make sense to have the directionality on the other way around. So in this case, you can use the common sense just to say that like some of these I equivalents can be rejected based on what we know. I also mentioned something toward the end of the talk that sometimes assuming that there is no unmeasured confounder and assuming that the model is correct, for example, under linearity assumption, some of this ambiguity can be resolved, like assuming that, for example, like X, you want to resolve X, whether X is causing Y or Y causing X. If there is no unmeasured confounder, if at most one of the variables is Gaussian, you can resolve that as well. But in general, the general answer to that is that you can't. So you need some sort of like either like partial knowledge and not all of the causal question can be answered from observational data in the most general case, but sometimes we have access to this knowledge.
Yeah, I guess that's also somewhat the beauty of working at this intersection of causality, machine learning, and medical imaging. It again highlights how important it is to bring in different disciplines and domain expertise and domain knowledge, right? So, I mean, we cannot just sit down and come up with our assumptions about the real world. We really need to talk to the experts who might bring in their own prior knowledge. There was a question, I guess that is something we can solve offline, about the proof you have been showing with the non-Gaussian residuals. So I don't know if that was solved already.
I think like I sent one reference that I think it is discussed. Don't quote me on this, but I think the proof goes like this. So let's say that X causes Y, right? So if X causes Y and assume it is linear, so Y is equal beta X plus epsilon. So now for a second, assume that both X and epsilon, which is the noise, are both Gaussian. So if they're both Gaussian, beta X is Gaussian, epsilon is Gaussian, sum of two Gaussian is Gaussian. And so I can still change the beta a little bit and push that to, because X and epsilon are independent, I can push a little bit of beta and then put it into distribution of the noise and it's still the same model, so it's not identifiable. So you need, so the reason that both of them cannot be Gaussian is that some of the Gaussian is still Gaussian, and so I can push the weight around and assume they're independent, change the variance of the noise and still get good fit. I think that's how the proof goes, but I sent one reference that I'm presuming that's discussed there.
Right, thank you. I should emphasize, so we are recording everything, and this will be available on the Pathable website. It will take a bit. So after today's session, I think it takes 24 hours until everything becomes available again. But these things will be available. Although the chats, not the Zoom chats, but the chats in the Pathable website will stay alive. And I'm sure everyone here is happy to continue monitoring those, or otherwise reach out to us if there are follow-up questions. In the interest of time, I would like to move on to the next session. There was a question for Christine regarding counterfactuals. And I want to delay this a little bit to the session after we have discussed counterfactuals. But Kayan and Christian will be also around for later for the other Q&A session and also for our roundtable. So at the very end, we will have an open discussion where we really invite everyone to join in. So let me conclude this first session. Thanks again for Kayan and Christine for giving us the background that we need. And now in the next session, we will talk about causality more in the medical imaging setting.